audible? Yes. So let me just connect to uh, class. That would be okay. So hello everyone. In today's class, we will be. This is week 11 of the course Transport Phenomena for Non-Newtonian Fluid, and as you know that the transport phenomena involves transport of all these species, different species. Here we are discussing about all the processes of motion of any species or heat or mass or momentum. So, fluid mechanics, heat transfer, and mass transfer, all the three subjects are equally used in this particular course, and simultaneous effect of all these events in any real life system we are dealing with. So, in this particular week, what we have mostly discussed, the topic was about this quasi study analysis. Okay, so quasi study state analysis we have done for processes involving heat transfer, mass transfer, and chemical reaction, and mostly heat transfer and mass transfer together, right? So we will be uh, revising whatever content has been taught in week 11. Along with that, we will be solving some questions related to the topic of the week, related to simultaneous heat and mass transfer along with the chemical reaction in terms of process state analysis, right? So I will be showing you some important aspects of this analysis, and then uh, there is one document that I have uh, had, and that is very well explaining why this analysis is important in terms of having some kind of assumption, but in turn it returns much or explains us some asymptotic behavior of the system. And then another one is this particular quasi steady state analysis that we will be discussing with some examples, and I will be telling you uh, very uh, in very simplified way what the analysis is, what is the advantage of this analysis, and where this analysis fail, and we have to go for the complete transient analysis, right? So let me just project my screen. Okay, so so show my screen. Okay, so this is week 11 of the post transport phenomenon non-Newtonian fluid, right? And if you see uh, that we started with this basics of non-Newtonian fluid, how it is differing from the Newtonian fluid, some examples of them, and then we had different models for the non-Newtonian fluid, and mostly from the last week to last 2 or 3 weeks, we are looking at we are mostly dealing with the transport phenomena or simultaneous transfer, mass transfer, momentum transfer. We are not having much of this non-Newtonian part now, right? But it can be included. The procedure will be same. Just we have to go for some numerical methods or some sophisticated softwares like Mathematica that will be helping you to do the tedious equations and deal with them, right? So, so these are the questions that we will be solving in this particular lecture. and this class will be helping you in solving the weekly assignments. Along with that, it will help you to get yourself confident and get revision of whatever content has been taught in the week. And I will be using this teaching and learning material on the quasi steady state approximation and partial equilibrium approximation. So by this person also et al. And the team. So we should acknowledge them. And then these analysis I will be explaining you step by step, and then we will be solving the questions. Along with that, we will be going through the content of the week. So far, if you know that this, if you see this one, then you will come to know that we are here. So we started with this course in the week one. Mostly we had this uh, particular basics one. Then rheological instrument week 2 and 3 we did, and then week 3 equation of change for motion and for isothermal and non-isothermal we have done. Then flow through pipe for different power law models you did. Laminar to turbulent transition, that uh, analysis we have done, the critical analysis. And we have also discussed about packed bed dispersion in the packed bed and liquid fluid, liquid solid fluids about power materials. So for nanotubes. Free convection between the two plate, discuss heat generation and temperature distribution in the confined between coaxial cylinder. These things we have already done. Temperature distribution, pipe flow with the thermal effects we have discussed. Then combined with chemical reaction also we have discussed about transpiration cooling. And week 10, the last week what we have done is this uh, basic mass transfer, what are the things, and under the non-isothermal effect how the mass transfer will be actually uh, getting changed. The extent of mass transfer will be how that will be coming up in the picture that we have seen, right? So, so the thing is, now if you see this week 11, here what we are dealing with is quasi-steady analysis of simultaneous heat transfer, mass transfer, and chemical reaction. And after that, there is three part which is involving heat transfer and mass transfer. Only the first part is involving chemical reaction, right? So these all the concepts we will be revising, and we will be solving some question around this, right? So before diving into this particular lectures, which is 35, 36, 37, 38, around quasi-steady analysis of simultaneous heat transfer, mass transfer, and chemical reaction. In this, if you actually see what is the more important message is, let me just set it here. If I can set it. So, okay, so let me just. Okay, so the if you see basics, we will go first. Before that, we see this what it says. Let me just expand it a bit. Okay. What it says: quasi-steady analysis of a simultaneous heat transfer, mass transfer, and chemical reaction is an engineering/physics approximation method used when multiple coupled processes occur together, but one or more of them involve much faster than others. So in that case, we will be using, and we see that these are happening simultaneously. The mass transfer reactions, the flow of the species, flow of the fluid, those are happening together, right? So now this become very important that when background about this is when when chemical reaction occur in a system, for example the catalyst, gas solid, liquid solid, or within a porous catalyst. It is usually coupled with heat transfer due to release or absorption of the reaction in the mass transfer. Because of the reactant product must diffuse, convect to or from the reaction site, right? So in reality, all these processes are transient and strongly coupled. Okay, so they are happening together and they are coupled, and that is the main motto because of which this subject transport phenomena came into the picture from this word Stuart Lightfoot, the very famous book. It is combining all these three subjects together and teaching you any problem with this combined approach, right? So in reality, all these processes are transient and strongly coupled, but solving the fully transient system of partial differential equation, which is for the energy, for the species, for the momentum, and for the reaction kinetics, is often intractable. They are a bit tedious, right? So for that, because of that reason, this quasi-study analysis came into the picture. What it does is, the idea is to assume one process is much faster than the overall rate limiting process, right? And thus reaches a pseudo steady state almost instantaneously compared to the time scale of the interest, right? So the idea is assume one process is much faster than the overall rate limiting process. Okay, and thus reaches a pseudo steady state almost instantaneously compared to the time scale of the interest. Okay, so these are the heterogeneous catalysts. For example, chemical reaction engineering. Second, there is two parts: first part and second part of that. In the second part, where we learn about the catalyst, those things, CRE2. In that, we see that heterogeneous catalysis and how these equations are made for them. So mass diffusion inside pore may equilibrate very fast compared to the catalyst heating or overall chemical conversion, right? So the mass balance inside the particle can be treated as a steady state, even though the whole system evolves in time, right? So mathematically, you can write that inside the catalyst there is this del C by del T is approximately 0 and del T by del T time approximately 0. So concentration temperature both are constant. For the faster variable, while the slower variable evolve. Okay. For the faster variable we can do this, and for the slower variable we can do that. This reduces the governing equation from PD to ordinary differential equations slash out that can be for the family algebraic equations, right? So this application in heat transfer mass transfer reaction, how it is applied, it is typically in combustion catalytic reactor packed with drying polymer, etc. In quasi-steady analysis, species diffuse inside a thin film or boundary layer can be considered quasi-steady. Okay, temperature profile. Temperature profile in small particle can be assumed quasi-steady if thermal diffusibility is very high. Okay, so schematic number is here. Okay, UCP, right? Right? UCP, so that thing. Reaction rate can then be Peclet number and schematic number. You look at that. Reaction rate. In the previous lecture, we have discussed about those non-Newtonian numbers. Reaction rate can then be expressed as function of steady state concentration and temperature, right? So reaction rate can then be expressed function of steady concentration and temperature. So that's what you are going to do. For example, in reacting porous catalyst pellets, okay, what is that? Here, this is species balance, which is quasi-steady state. Here you are writing like that. This is because of the diffusion. and this is the reaction which is taking place equals to 0. Energy balance can be written like this. This is overall reactor balance. We still understand. So why it is useful? Simplifies analysis while capturing the coupling between heat transfer and reaction. Allows definition of dimensionless groups, Biot number, Thiele modulus, Dampoler number, Lewis number that indicate which process controls the overall rate. We will be looking at these Lewis number. While used in ignition analysis, heterogeneous catalysis, drying and combustion stability problems. Quasi, it is very important this line, so let me just make it font side. This will summarize you everything. Okay, so quasi-study analysis of simultaneous heat transfer, mass transfer means treating the faster transport process as if they are instantaneous stability with oral conversion of the. This allows coupled reaction transport problem to be simplified into study equations, which still accounting for the still accounting for the interaction between the reaction and right. So these are some examples that we will be discussing in the course of this particular lecture. So the distinction between this quasi-steady state and complete transitions analysis is subtle but very important when you are modeling solution in master spectrum. So for example, complete transient analysis, you see, you solve the full time dependent governing equation for the concentration, for the temperature, and also for the velocity field. And these are wave partial differential equation. So it is needed if bulk fluid condition changes rapidly, step change in inlet concentration temperature. Reaction start ignition is time scale of the diffusion heat transfer. Those most accurate captures all the time evolution computationally heavy, so it is difficult requiring one consideration, right? But in steady state analysis, what is that? You assume all the time derivative vanishes everywhere, both inside the pellet and the bulk. Okay. Interpretation: system has reached final equilibrium where heat generation equals to heat removal, mass consumption equals to mass supply. Long time behavior of a reactor or catalytic pellet under fixed operation condition you can see. And those is what simplified to ODEs or algebraic equation cannot describe startup transitions, oscillations, transients, oscillations, ignition, etc. Quasi steady state we have already discussed. It is hybrid approach. Some processes, the faster one, are assumed to be equilibrium, create instantaneous related to the slow time scale of interest. Their governing equation are set to study from locally, even though the whole system is not yet at steady state. And examples are inside catalyst pellet, diffusion and convection may be very fast compared to the overall bulk concentration change, right? And then the second point is, so inside the pellet use some study partial differential equation for this concentration and temperature as a function of R in that pellet, the ball. But the bulk concentration temperature may still be governed by transient levels, right? So now this mathematical flavors inside we will have this one. We have seen these equations in this third week, I think, where this knowledge is the fourth week, knowledge is the equation of states we have defined, right? And the bulk we are considering this to be. So when it is transient occur mainly at the large scale, bulk of the two running by manifest becomes much faster. This separation of time and scale justifies keeping this system. Those much simpler than the full transient, but still captures slow dynamics at the microscope. Widely used in catalysis, Drying, aerosol chemistry, droplet combustion, etc. Absolutely break down if internal diffusion and heat transfer are not much faster. Not faster. Okay. So these are some differences that I have listed out. The time derivative here you are including. What is captured, startup and study behavior oscillation, everything you capture. Typically used initial extinction study process control complexity it is very difficult and study set you know neglect everywhere time derivatives final equilibrium state of unity will capture long time operating condition analysis will be judged and to closed. Essentially it is moderate neglect only the past process slow evolution of system by fast internal process catalytic pellet droplet thin film where obviously the heat adsorption is faster than the bulk changes. So in that case process will be used and then moderate. Beautiful. Okay. So now in few lines if you want to learn this, it is if the transient is it will solve everything in time and it is most general but most complex. Steady state is what? It is when the time is tending to infinite, everything settled, then it will solve and it is easy. Because a steady state is what fast process treated as if it steady at every instant, while slow process still evolve in time, right? So that's what we have discussed and we have seen so far, right? So the question one. So what I will be doing is I will be projecting question and then so this was enough about this basics of this particular problem which is quasi steady state analysis and now we will be moving toward the question. So our first question is this one. So here the option A is C, B is here, C is here and D is this is D. Okay. So now okay. So this is xi infinite and this is t infinite, right? We just fix it. It is xi infinite. Okay. Okay. So if we can increase it, okay. So consider combustion of spherical particle in the presence of oxygen at a certain high temperature, right? So one spherical particle is there, right? Let me just check it. One spherical particle is there. Okay. Near oxygen. It is spherical particle. If this is going to combustion. Okay, that was nice. Particle radius is r and the combustion is taking place very soon. Is it happening? Okay, very slow. So that the pseudo study approach can be applied. Uh, so you can use this pseudo quasi study approach. Okay, mole fraction and temperature. So here T infinite and this x I infinite is this. Away from the particle is done. Reaction is very fast. Combustion is very slow. Reaction is what? Very fast. The particle is small enough that particle is small is better than the one both for HT and MT. What is generalized energy balance equation and the surface area? So this is the question that is answered. Okay, so how you are going to solve it? How you are going to solve it? It is the generalized. This is the document that I am talking. This here, these two approximations exploiting evolution at different time scales are usually used to simplify rate laws in chemical kinetics. The quasi-steady state approximation, which is QSSA, is used to eliminate a species which involve faster than the other. Okay. And another one is this partial equilibrium approximation. It removes a reaction step associated with the extent involving faster than the other. Both methods are adiabatic elimination of one variable. So you can go through this particular document. I will be adding up with the link. And here one example is given for this quasi-steady state approximation, the series reaction of this chemical reaction engineering. The same calculations are over here that we study in chemical reaction engineering. And here the most important line is this one. This where this quasi-steady state approximation to okay. So and another one is partial equilibrium approximation that you can read for your next. Okay. So if you find them on the kind contribution, right? So let us see this problem. So this particular similar example we have had in our lecture. Okay, so if you know about the problem that we have solved, then you can easily understand how this will be solved. Right? So let me just take the slide so that I can explain. Okay. So yes, yes. If you see this one, exact same problem we have solved. Here one particle, carbon particle was there, and here also this xi infinity was this at the far bulk, T infinity is at this, and this particular reaction is happening, right? So in this one, if you remember, this particle, this question was what? Combustion of the carbon particle. So you wrote this some reaction is not there, but again The basics are same. So combustion of the carbon occur primarily through this reaction. Carbon will have this half mole of one mole of carbon will have this half mole of oxygen, and it will give one mole of carbon monoxide. Considering a spherical carbon particle, these are suspended in the gas mixture under the pseudo-steady condition. Assume that the gas contains only oxygen and carbon monoxide. B and oxygen is a mole fraction we have seen. Reaction is very fast and the particle is small enough that the proton will both into mass and molecules. So you are asked these questions. So determine the fluxes at the surface and relate reaction to change in the radii of the particle, right? And then determine oxygen flux at the surface, which is NMR. Relate the heat flux and reaction rate at the particle surface, and then determine the particle temperature. So the D part, which is determine the particle temperature, because in your question, if you see, you are asked about what? You are asked about what is the generalized energy balance equation at the surface of the particle. So in this one, determine the particle temperature. So it is at the surface of the particle. So here we have had those discussions. So let us come to the slide itself. Okay. So if you see this one, so in this one, if this heat flux and the reaction rate at the particle surface, if is interfacial energy levels, so you are not considering radiation in this case. And this, you will remember the week 4 of the course where this non-isothermal equation will be right, and you had this ER. So this ER is having effect because of everything, like viscous dissipation, because of the pressure energy, because of the reaction, because of the source. If there is, if the reaction is endothermic or exothermic, because of the flow, convection, and instead of the viscous dissipation, that is the heat. So everything comes up into the ER. And if you see that this is a particular thing that is asked in the question. So let me just snip it if I can. Okay. You can put it. Good. Okay. So, very important. So I will keep it in the slide also, so that you can follow it whenever you are actually doing with this. So it is dr minus summation of Ci Hi dr by dt r at r plus. So it is r at a surface just inside it and outside it. So dr minus Ci Hi ds by r minus. Okay. This r plus and r minus I will be telling you. Okay. So this one is correct. Okay. So A is correct. Okay. Now, if you can just revise it again, so that is so, so, so if you remember this one here, what you have taken is this just before or just after this r plus and r minus. So r is the radius of particle. Just inside r, inside you are writing that energy, and outside that you are writing that energy, and that is the one we have properly discussed. Okay. So here what I am saying is, in this one you see, so something here is r minus and something here is r plus. Okay, that's what is so that is it for this particular question. Next question is Consider combustion of a spherical particle in the presence of oxygen at certain high temperature. Right? Particle radius is r and the combustion is taking place very slowly, so that pseudo steady approximation can be applied. Okay, so particle radius is r and the combustion is taking place very slowly. Okay, let us move here. Mole fraction xi infinite and p infinite for away from the particle are known. Reaction is very fast, so the particle because of high temperature particle release is high. Here you are having this 2 unity at side infinite. Reaction is very fast. Very fast. The cell is taking place very slow. Small particle. Heat is for heat transfer and mass transfer. Combustion is moving. Okay. That oxygen is denoted by A. Like in that problem we have discussed what is the oxygen flux at the surface. So if you see this is oxygen. So if you see this oxygen flux with the flux at the surface and reaction. So if you see the options, so this is having this Na, C, DAB, DX, this one. Okay. So let's write these options A, B, and C. These are three options. So this is very similar one that we study in the diffusion, right? So since Peclet number is less than 1 for the heat transfer and the mass transfer, and you are saying that oxygen to be denoted by A, okay. So in that case, if you see that this for the oxygen interfacial species which follows a strict code, okay. So it denotes gas quantity evaluated at the surface, i.e. R plus. For the carbon, it is given. Let's see for the oxygen. So for the oxygen, you see this. Okay. So Na, so R plus at R plus just greater than R. We are having this N equals to N0. And below that only pure carbon is there. So Ca is 0 after that because fast reaction. So whatever oxygen is used, that will be not there. It will be used by this combustion carbon. Okay, so concentration flux of other components should be 0 here. Okay, so in that case, if you see the main thing, so for the oxygen, if you see the standard process that you follow, okay, is the one that we always solve, right? So let me just put that here. Okay. So oxygen flux at the surface, oxygen flux at the surface. So this said take it as A. So I is suppose this is initial concentration energy. Okay. So for that you are going from this diffusion NaR for this spherical unit. Okay, so if you simplify it a bit, okay. So for this case, you know that for the combustion of the particle, and in this case, you have seen that in this combustion, high concentration. Okay. So those things are there. So if you see this, so this, okay. So here this is correct. You getting? To see his answer. Because once you solve it, it's very clear. Once you solve it, once you solve it, these steps, and you know that for your case, this combustion, this half mole will be supplied, right? C plus half mole gives C. So in that case, if you see this, this will be 200. Because here, so CO is component B. CO is component B. So it's so in that case, if you see that, then you can solve it, you will get it. So you will get only equals to from there when you put it like this, you will be getting MAR equals to y1 plus xa will be xa over here. And this is for the particle that we are discussing. Okay. So this is done for this second question. Let's save it. So if you see this from the beginning only, if you can have the result of this particular 35th lecture, because rest lectures are same, because in the 35th lecture we had this discussion of this heat transfer of sulfur and chemical reaction together, so it becomes very easy for us to then appreciate this. Okay, so this reaction is opening at the surface and outside is gas, carbon is there, and R is this radiation. Then at the bulk we are having these conditions. So first writing the species balance for this carbon. Okay, so R plus the species flux and R minus the flux, and that will be actually happening, changing based on the reaction. Okay, so from here you had this dr by dt. equals to this. Add R plus, you have this carbon molecule, so NCl and CC will become 0. So everything goes out. R minus, you are having NC 0 because pure carbon is there. So from here you will have this minus D, CC, TR, equals to 1C. So this first expression we have. This very important first piece expression we have. Okay, so let me just uh, put all the important equations. So this one, equation 1 is a problem. Is gave you for carbon plus equals CC. Okay. And for oxygen, similarly, we will get Na 0 equals to minus. Similarly, this one. For carbon monoxide, you will see here that will come out. Carbon monoxide. So for that, this MB not R plus. Okay. And CP not. Carbon only pure carbon is inside the particle. Okay. So concentration of the first and other compound should be 0. That's why other companies use 0. Okay. So this will be equals to what? RSB. So such small question can come. Okay. From this stoichiometry, you understand this reaction stoichiometry is RS. This R S I, which is at the surface. S I is A B or carbon. Okay. A B or C carbon. So based on that, you are having this RS related to different component A, B, and C. And then combine the differential currents. You can use for instruction information. You can do that for the surface for this oxygen and then try to do this species conservation. Okay, this was there. This standard equation. You see this standard equation and the concentration. In this one, what you got is this will give you this oxygen, right? This resistance will be 0. RSA. So based on that, if you solve it, you will get R square NIR equals to FT. So it will be a constant, but this constant will be depending on time that we are considering, and we are considering the original concentration in the fossil steady state, right? So because of that, this will come out, and now when you use these equations together in this one to evaluate the constant, okay. So with the given boundary condition, finally we are going to get these equations. Okay. So that is it for this particular question. So again, you have considered the temperature and the reaction potential. So because of that, some EDS equations are coming in, but these are similar and very easy to deal with because under this quasi study approximation, things become a bit clear and easy, right? So the next question is what? Let's see. Okay. So say this is consider a vertical cylinder of radius r and height h. Okay. The radius is r, height is h. Okay, so in this case, and it is filled with pure organic liquid. Initially, it is open to the air and evaporation begins at T equals to 0. And evaporation is lowering gas liquid interface. So this is gas liquid interface. Gas liquid interface. For simplicity, air is viewed as a single component so that diffusion in the gas is binary. Air and organic components are denoted by A, B. Organic component is denoted. This is the organic. Important assumptions are this one. Okay. So when you know mole fraction of organic at z equals to 0 is constant. It is denoted as x air above the container is assumed to be well mixed and to contain a visible amount of organic such that x b, this is very important, such that xb st is equals to 0. Air above the container is assumed to be well mixed and to contain a negligible amount of organic such that xb st belongs to 0 and okay. There is organic as as it is as we had any at as we zero. As we is 0 at the interface it is 0. And this interface if it is changing then also assume no air enter or leaves the liquid as would be true if the organic were the liquid enter. Okay. Assume no air enter or leave the liquid as the organic. What is the equation for instantaneous fraction B? Where in the column of anywhere. So what I'm saying is, if you see this, this will evaporate, what will happen? There will be another state coming up into the picture, where this interface is coming and suppose it is here. So this initial from the initial position. This one, this is the height h. So what it said initially at time 0, at initially the mole fraction of the organic vapor at z equals to 0, z equals to 0 is what? Denoted as b. So x b 0 comma t equals to x 0, right? And this x 0 what is here already h x b 0 h comma t is 0. Okay, now here is so how you are going to solve it. So exactly similar problem we have discussed in the week second of this course. Okay, so let me just week second of this week second of this week. Okay, so in this one, if you see, the problem is what? This is Quasi study 7 last answer. So here, evaporation of column of the liquid, right? So let's discuss it completely. Then it will make you comfortable with this, which is around this. So consider a vertical cylinder of radius r, okay, and its radius r and height h, and is filled with the pure organic liquid, supposedly acetone is there. Okay, so this initially it is open to the air and evaporation begins at the t equals to 0, right? Evaporation is lowering gas liquid interface, so this interface is moving down, like I said, by amount ht that increases until the liquid is gone. So z equals to 0 is chosen as origin, which is gas liquid interface, right? For simplicity, air is viewed as a single component so that diffusion in the gas is binary. So that we have discussed. So you see, this is r, this is z equals to 0, this is z equals to ht. So any height, whatever height you want to use, this is h. Okay. So let A is air, B is organic vapor. Mole fraction of the organic vapor at z equals to 0 is constant and is denoted by this. Air above the container is assumed to be well mixed, and assume no air enters or leaves the liquid as well would be true if the organic will be this. What is the time at which the equation will complete? So this is very similar question that we are having now. Just that in that you are asked about this only this. You are asked about what is the equation for instantaneous flux of B anywhere in the point. Okay, so that we will be discussing. But what I am doing is I am putting all the necessary slides here so that you can have. This will help you in revising the thing quickly. Everything is at one place, right? So let's take it. Yes. We will discuss it at the same time. We will put it there. Okay. This is the question that you are dealing with. Just that in your question, the main point that you are asking is this one. Okay. So you know that this problem is slightly different from the diffusion through a stagnant gas film as interface is moving with the time. So here interface is moving. So we begin by supposing that the pseudo steady analysis is valid in the absence of time derivative and or in absence of chemical reaction. Ma z and mpz are each independent of z. Okay. So this is the assumption that you are making, that this fluxation Lz and Lz are each not depending on z in the absence of time derivative, right? So this expression, if you see, for the flux, for the reaction, and then this Lz differentiate because of time, and when you expand it like this to this, what will happen? You are considering it steady, so it will go zero, and then you are not considering this reaction, so R is zero, and then this one, see this one, whatever change you are considering is happening in Z, the column. So this del and then Z by del Z equals to 0. So you are saying that this is not the function of Z, so it must be function of time. Okay, let's see. So it is an as a dz equals to 0. Similarly for the B component, you know, combined mole flux on B is what? So this one. Okay, so you are asked about the same. Let us see. What I'm saying is, yes, this one. So the flux of B is divided. That was the question. So just put it there because at least see the things they have to be examples. If you see this here, so these all are in terms of this. Okay, so see, you see, it is depending on ST. So unit wise also you could have eliminated these things. So del Z is there, so you cannot eliminate this one. These things, but just see the final expression that came. Okay, minus C dAB ST. So flux of B decreases over time because of unit distance in the gas. Okay. Okay, that is a top container. So, but this relation cannot be used as a complete form because solution, because this ST is unknown. So let's say it is minus C dAB ST and then 1 minus ST. C is correct. So third question is done. So this was second lecture, right? So similarly, this for this HCM, the interface flux balance will be useful. So for this HT now you start doing this interface balance add interface for 0 minus 0 plus interface, and finally what you get is this one, this HT. How it is showing you the time you calculated. So you got that this H varies with root of time. Okay. So this root of time you are able to see. Now The total time of evaporation also you calculated. Okay, this one, the total time of evaporation, if there is this L0 is very low, the pressure is low enough, then in that case. So these equations can be used for this. There are these equations based on these equations can be used. So very general equations you can remember, right? After that, you had discussion about this melting of spherical crystals, right? So, so that we will be discussing about melting of spherical crystals. Okay, so let's first solve the problem then so there is this. Yes, so it is given. Okay, so consider a vertical cylinder of radius r and the height h and is filled with the pure oil, right? Similar system like last case. Okay, so with pure organic liquid, initially it is open to the air and evaporation begins at the t equals to 0, right? Evaporation uh, is starting at t equals to 0, so evaporation is lower, lowering gas liquid interface by the amount ht, like there is last problem we have seen, that increases until the liquid is gone. It is complete evaporation. The time required to complete evaporation of the liquid is 2 hours. And the height of the column is 1 meter. Right? Time for the complete evaporation is what would be the time required in our complete evaporation. If the height of the column is 2 meter, it's I think the same as the height of the column of the. Okay, so this could be solved. So it is very easy. You see the expression is given. If you remember the final, so let's see it. Right? We require this proportional to our analytic square of 1h. Right? So based on that, you should see that suppose t final t is equal to h square. So when right? So what we will get. So it is taking 2 hours. Okay. So the thing is, if you want to see this problem clearly, I mean this, if you see, it is taking 2 hours for evaporation in lowering gas liquid interface by an amount S2 that increases until the is S2 that increases until the liquid is gone. The time required to complete evaporation of liquid is 2 hours. And the amount of carbon is 1. So from here you can calculate the value of this. Mistakes. Okay. Now, what will be the time required for the evaporation? Is 2 meters. It is 2 meters. And what is the condition? 2 meters. It is correct. So the height of the column will be 2 meters. It will take 8 hours for the evaporate the ions, right? So that is it for this particular question. Now let's open the slide. So now another topic is melting of spherical crystal. How it is melting. About that diagnosis. So next 8 slide we will be looking at how these type of problem will be solved. Okay, so melting of spherical crystal is assume that spherical crystal of initial release R0 and the temperature T0 is immersed in a large standing volume of the same. Okay, so there is a liquid, there is a crystalline sample. So melting temperature Tm is system is such that Tm is between this Tn or infinity. So there will be okay, so that the crystal is immediately begin to melt and the latent heat of this frequency. Okay. Okay, so yes, for simplicity, assume that the solid and the liquid densities are equal. Thus, there is no tendency for the crystal to rise or settle due to flow. Another one is this: the crystal immediately begin to melt and latent heat for melting or gases. Okay. The things are given to you. Now, select center of the crystal as the origin of the coordinate system. Assume symmetry so that it ensures that T equals to TRT. T is the function of radius. The radius it is liquid velocity has at most a radial component that is there is no need for this spherical angles. Done by your magazine. Obtain the time for the crystal to melt. This is the question that has been asked, right? So, so this is the crystal that is the liquid. Bulk liquid is at T infinite, and then T equals to what? T0, right? So, so surface temperature you are having and initial radius you are having. So solid liquid interface. If you see, okay, solid liquid interface. Solid liquid interface moves towards as melting proceeds. However, according to E equation of continuity, we are equals to 0. So that we are proving again. So equation of continuity, if you write for the spherical coordinate, you can take it from this polyester type or any standard book. And then if you see there is no this angles involved in this particular as per the assumption that we have made here. The last second point, there is no need for this spherical angles. So now this del by del r square v r equals to 0. Very important. In most of the problem you will see this equation, right? So here if you see this everywhere in the system r square v r equals to c, right? So it should be constant. Okay, so and you know that since r square v r equals to 0, it is given in this scenario at r equals to 0. When radius is 0, there will be nothing. Okay. So then c comes out to be 0, and based on that you will have this. If so this Vr comes out to be 0 for all the R. So everywhere in the system of the both liquid and the crystals, okay, and according to heat transfer in both the phases by conduction only, it is happening. You will see that, right? So now determine RT, which is radius, and melting time, which is TP, assuming pseudo steady condition. So you will do interfacial balance for this at the center and at the this L. Okay, liquid is, and this will be given only by this little bit of the vaporization melting, so when you manage this, and you know that this is what this is change in the radii of this melting point, right? So now this heat energy balance equation in the spherical coordinate, if you write and you do the juggleries over here, so this is pseudo steady state approximation delta by delta equals to 0. It will give you the C1. Based on that, you can calculate C1 as delta by delta equals to 0 and equals to 0. It will give the value of C1. Okay, and this is 0 everywhere in the crystal, so QRC equals to 0. Okay, so QRL becomes this minus KL del T by del R, right? So from this equation, if you see this one, and you know our you both phase by conduction only. So this conduction in the both phase you are assumed, right? So for the gases or for the liquids you have seen in some problem we have wrote this K dt by dr dt by dx for the gases also. Though it is meant for the solids mostly, but in this case you are assuming that because those are stagnant, having much conductive part associated with them, right? So in that case, if you see this del T by del R equals to 0 everywhere in the crystal. So just doing this, the release now this equation finally comes up. So after solving one, so this is 2. Now heat uh, flux from energy equation for liquid. You had this one. And when you solve it, this R square del T by del R comes out to be constant. This will be that this will comes out this. And now you know that T equals to infinite, R equals to infinite, T is T infinite. So C3 comes out to be T infinite. And at R equals to RT, Tm equals to C2. It is melting to Tm equals to C2. So you will get this one. C2 you get. Tm, this is R. This is RNE variable. Okay, but the surface there will be melting temperature. No? So now accordingly you had this T, you can calculate out del T by del R, and del T by del R is this one. Now this del T by del Y we are going to we want to calculate this QRI, right? And now very easy steps are there. You can put this one here, QRL here, and this del T by del R everything here to calculate this R, which is comes out to be this one. R comes out to be this one. Intermediate radius and initial radius and now melting time is defined as when R is 0. So you put R is 0 and then whatever value you will get for the time, that is the time for melting. So what you observe that time for melting is proportional to the square of this radius, right? And we have also observed that this in the column 1 that time for complete evaporation was like this, right? Right. So that is it. So let's open the next problem. That is solve the fourth one. Fourth one is done. Now the fifth one is this one. C. Assume that the spherical crystal of assume that the spherical crystal that crystal of initial radius R0 and temperature T0 is immersed in a large turbine volume of same T infinite, right? So let's okay. Melting temperature Tm is such that this we can fix it. So these are typos. It is to fix that here itself. Okay, so the time required for complete melting is so that the crystal immediately begin to melt, and the latent heat for the melting is this one. That time required for complete melting is. So this we have solved right now. The decision that we have made, that was the same. So if you remember, we have seen that it is depending on R square. So so when the initial radius is, so let's this is working is R0. So now if you see this, when the initial radius is 0.01 meter, the time required for the complete melting of the crystal is 2 hours. So if you use this expression, it will be pseudo lambda r square. So it is said it is 0.01 meter, 2 hours. Okay, 2 hours for what? 2 lambda. So from here you will have this factor. Suppose this factor is x. So what it says is, the initial radius is double, then the initial radius is double, the initial radius is double. So t equals to x times 2 times of 0. So this x you so what I'm doing is 8 will be the answer. 2000. A is correct answer. Okay, so A is correct answer. Now moving towards the next problem is this one, right? Consider evaporation of small droplet of consider evaporation of small droplet of R0. Okay. Suspended in a dry nitrogen gas stream. Okay. Temperature and the composition far away from the droplet are T infinite and X infinite. Right? respectively, uh, with I equals to N for the nitrogen, I equals to W for water. Coordinate origin is chosen at center of the reactor. Assume that the droplet radii RT changes slowly with time, so that a pseudo steady model can be used. RT changes slowly with the time, so like this. So evaporation of this small droplet is happening, which is having R0, suspended in a dry nitrogen gas stream. Temperature of the composition found in the droplet is T from 1 at 7. Okay. Time so that the pseudo time required for the evaporation is assume nuclear number is very small. So this problem can be reduced into one involving steady diffusion conduction in this condition. The time required for the evaporation of the droplet is 32%. So here it is given that, right? When the initial radii is equal to and the total evaporation time is 0, what is the time required for the total evaporation of the radius is equal to R. From here, if you see that is divided, so that you can get it is reduced to 1. So this can be seen this. So the this can be what so from here what will happen? You see. So let's see the derivation of this. Then we will see. It is very easy. So let us just complete it. So put this 0.2 here, or you can just do that. So, saving this. So T is equal to R 0 squared. So now we say radius is 0.02, the time is 2. So 2 hour is 0.02. 0.02 raised to 10 meters. Okay. Now if so get this concept here or else there's another one is x equals to so 3 by x equals to Okay, so let's see this question, the slides. It is how it has been explained. Okay, so let me just fix it here. See this 37 slide, freezing of salt water in the discourse. Last one, this one, this one, what? This one, what? So this one, what? This was basically time for completed operation, right? So the time for completed operation is like this particular operation. So this also we have solved. This 38th lecture we will revise it. 7th lecture I will revise and I will see will be some important points in that, and then we will solve this particular. So still we are having 20 minutes, so 10 minutes each, 5 minutes and 15 minutes we will discuss these two slides, right? So we'll let you please see what are the main basic points that I have already told about the pseudo this one. Quasi steady state. So I will again project these key differences slide that we have already discussed. Okay, so these were the slides that we have discussed. I will keep it in at the end of this particular. So you please look at it and revise it. So till then you revise it. To keep revising these points, the differences between steady state, transient, and this quasi steady state analysis. So I hope you have again gone through this, and then you have saw the things that we are right now doing, like this simultaneous mass transfer and heat transfer. One is fast, one is slow, and then you are making this particular assumption of quasi steady analysis. It is a bit uh, moderately difficult as compared to the steady state, but yes, it gives a lot information about the same system, right? So let's see this how it is done. So here you are having this evaporation of water. So there is one uh, small droplet of known radius suspended in the stream of nitrogen. The temperature and the composition far away from the is given as T infinite and Xa infinite. Okay, with I equals to 10 for nitrogen, right? So, so you have solved this. Now, one more question we are going to solve. I will be rather giving you, and then I will ask you about that. So, the question is, question is which of the following is correct for the freezing of salt water, freezing of salt water, and the conditions are, so I will be just putting the same conditions that we have used many times. Why I am putting this condition over there? Because this will save our time. So I am just putting it there. So you are having this freezing of water, freezing of salt water. These are the conditions, and now these are the another points that was there in the class you have been taught about. Okay. Okay, so now in this one, what you are given with this is freezing of salt water, right? The salt solution is here outside, and this salt solution is what? NaCl plus H2O, right? And now P equals to T infinite and Cs equals to C infinite and R equals to infinite, right? So now this, you see, this is RT, and then I is forming. So it could be anything. For example, it could be pure S2 or it could be S2 containing salt, right? So in this case, there are several things that we have seen. Okay, so I will be giving you options. Okay, so here option A is we are T equals to 0 everywhere as per the assumption. Is it true? B option is B option is change in the radius of the crystallization is KW thermoconductivity of water 3 rho W lambda r. Okay, so it is true. For the case where the salt is there, okay, for the case where the salt is there, this CSRT on the surface will come out to be NSRRT R square C infinite, right? The option is CSR comma 2 will come out to be C infinite by 1 minus R by ds dr by dt. Which of the following is correct? E is what? Or dr by dt less than 0. The C R comma T is greater than infinity. So these are the following is true. And the last option which is given here is what? Is so let's just leave it just this one. So last option can be later, but this one. So when you see and when you discuss it, you will get to know that which is correct or which is not correct. So let's revise this particular 57 side of the week. Right? So here you see these are the conditions, right, for this freezing of salt water. This problem involves a simplified model for growth of the ice crystal in the salt water. Right? Crystal which is pure H2O is idealized as a sphere of RT. Main effect of salt is that it lowers the freezing point, which is TF. Freezing point depression is described by expression is also given TF equals to T0 minus beta Cs, where T0 is freezing point for the pure water and beta is known positive constant and Cs is salt concentration. Okay, so far from the crystal T equals to T infinite and Cs equals to C infinite, and solution is stagnant. So for condition, assume that the temperature and the concentration field are both pseudo steady and spherically symmetric. For simplicity, assume that ice, pure water, and the salt solution all have same density. Okay, so use notations for I ice, for use for water, S is for salt, and L is for salt solution. Okay, so now these are the few points that I want to show. So using equation of continuity, you can derive that this VR equals to 0. Okay, so that's why the point A which is there is true. This one is true, right? This is correct. So if we will see this that here this salt. What is the role of salt that we will be looking at? But the point is this here. What it says assume for a moment that no salt is present, which will find dr/dt. So in that case, if you will see that for the case when pure water case is there and salt is not there, and you write this energy balance for that. So in that case, and simplified energy conservation, you know how we arrive to this on the last, like 35th method we see. So from here, this is not the function of r, so this must be function of something. We know that it is function of p, and then this del t by del r equals to this dr by kw, and it gives minus f by this. So now integrate it, use non-boundary conditions to find ft and other integration constants. So once you do that, at r equals to infinity equals to t0 to infinite, okay, and at r equals to r equals to tf equals to t0 this, the expressions, and you will have to put this here 0 because you are not having this solid effects. So finally, that you will be getting with this. For this CS you have removed. You see, CS. Okay. So now this is the expression. Option B is also correct. Okay. Similarly, the third problem which was there, if you see, now the case of the salt note that the temperature and the salt concentration in the liquid are equal to are unknown. Okay. As in dr by dt. So use conserve so use r and then you the temperature. So let me just see. So both are not known. So how you will say? So let us see that this particular doing the species and the energy balance there. This similarly, this species conservation equation about the salt you will this, and here you have this species conservation equation for what? Energy balance equation for this system. Okay. So from here, the FT, capital FT, you are considering, so use FT, the species that is given similar to the geophile that we had, and you will have this CSRT, C infinite 1 minus R by ds. So, so these two are correct. These two are correct. This is correct. And this is correct. So this is the slide 37. Seven is important. So this is one. And this is greater than, so this must be you see this is yes, this is so what you got A, B, C, D, and E, these are same correct. Let's discuss more about this particular problem. So if you see, when you use conservation of energy to get a second relationship on the unknown salt vector, so you see here, you are considering this temperature is changing with the R and time also. So this constant you don't know. So this constant, for this constant, if you see this, uh, finally what you are getting is this one. It is depending upon this HT, RK plus T infinite. Okay, and this HT we have already calculated here. RK P0 minus beta Cs R minus RT minus T infinite. So here we will get this. So we can see that the temperature is changing based on the salt concentration. Okay, inside the pan. So this inside this crystallized the ice which is forming from this salty water, right? So this is important expression. So we can put it here. Okay, so what I'm saying is this HT is calculated to be T0 minus beta CS R minus what? R minus T. Okay. T minus T. And in this one, the TRT, which comes out. HT here and rearrange what you will get. This is the function of temperature, right? Okay, so this is the one that comes up. So you can see so far we have solved question related to all the aspects. This was for salt formation, and this question was for this salty water forming freezing problem. We have discussed 37 lecture, and then this was about this evaporation of water droplet, small droplet, right? So it was the last lecture of the week. This was this uh, melting of this crystal. Okay. And melting of the crystal we have seen. Now the evaporation of the column of the liquid. So two problem I think we will follow. These are column of the liquid also we saw. We saw in this combustion problem, right? So two problem on combustion we have solved. So we can see that we have solved the sufficient amount of questions, and this completes the discussion of this particular week. That actually was very important in terms of let me just project this one. Yes, this was very important in terms of understanding. So let's not present now. Okay, so if you see this this quasi study analysis of simultaneous heat transfer mass transfer and the chemical reaction, and all the three parts that we have seen where the heat and mass transfer were coming together. The problem of this evaporation, this combustion of this carbon in oxygen environment, and then this evaporation of the volatile liquid from the cylindrical column, and then this crystallization uh, problem, melting problem, looking at the sphere problem, and then the very important one that we have just discussed, where this salt water freezing was there, that also we have seen. Was very important, evaporation of the droplet. So we have seen all these systems where this quasi study analysis becomes handy and helps us in order to analyze pseudo transient analysis of the system, right? So thank you so much for your attention, and we will meet in the next week, where we will be mostly focusing on the simultaneous heat and mass transfer, and momentum transfer, and mostly the boundary layer we will be discussing in the last week of the course. And then this after that there will be one more lecture where we will be revisiting or having some general discussion about the entire course, and then what are the questions that can be asked in the future in your examinations, in the final examination that will be, what are the topics are important, what can be made, where to focus, where not to focus, and how to approach your the entire week content in order to have overall understanding of the things that have been taught so far. Thank you so much.